good evening. So I will try to present all this, and I will first start by setting up what is particle physics and where we are today. Then talk about how we do in high energy physics, and in particular with the Large Hadron Collider, which is pictured on this photograph. So this photograph is taken from the Jura mountain, looking onto the Alps and the Mont Blanc. And on the ground, 100 meters underground, there is a tunnel of 27 kilometers of circumference. And I will tell you why this has been done. Then show how we detect particles, and I will take the example of the Atlas experiment and how it led to the Higgs boson discovery. And I will conclude by a few words on what is CERN and how it was invented and how it is run. So just I start with the standard model of particle physics and just position it here in the context of the universe. So you may know that the universe is somehow 30 milliard years old, okay? Starting from the Big Bang and where we are today. And with our experiments, accelerator at LHC, at CERN, at this Large Hadron Collider, somehow we managed to reproduce in what is important here, it is in a controlled way, meaning that we can reproduce it more than once, contrary to the universe, which was done once. So with this experiment, somehow we sit here with the energy we have today, which is something like 10 to the minus 10 seconds after the Big Bang. So a long time ago. So the problem of particle physics, which arose from the beginning of the century, but it started to accumulate in a complicated way by discovering many particles and trying to interpret that kind of picture. That was in the 60s, 70s. So you see cosmic rays and you don't know, you want to explain why all this is created. And at the end of all this campaign, and today, we have something we have found, observed, something like 180, more than 180 particles. And I will tell you in a moment that, in fact, these are particles which have been created artificially. Artificially, it's not true. They are not part of our body of the common mass, but they exist because they can be created by energy, by interactions. But for a particle physicist and for any person who wants to understand the nature of things, having so many is not acceptable. You can build, you can construct and understand how things are. So all the thematic, all the problem was to try to understand and explain these particles. And if you just memorize this, the sigmas now, these are some particles, because I will show an example in a minute, just a few of them, how they're made. So on top of the particles, in order to interpret how they are and how they behave, it has also, you have to link to interactions. And in our world today, we know of 4 interactions, the mean with which particles interact between each other. And this is gravity. Of course, everybody knows gravity. Falling, attraction of masses between each other, and the fact that objects fall here. There is the electromagnetism. Everybody knows, the light or thunderstorms. There is a weak nuclear force, which is at the origin of beta decay or the interactions in the sun. And finally, the strong nuclear force, which is the force which holds the nucleus of the atom together. So these are the 4 elementary particles, the 4 interactions with which all behavior can be explained. Today we haven't found any other. And in order one observes these interactions, now the way to interpret them and to describe how particles know about this interaction is through mediator. So for example, on this cartoon, throwing a ball to tell your partner that you're here somehow, and you transmit a force when you do this. So these four interactions are interpreted and explained by exchange of this mediator, these carrier forces. So for the electromagnetic force, it's a photon. For the weak force, these are the W and Z boson. So I tell you this and you have to trust me, and I will use them a bit later. For the strong force, it's a gluon, which keeps the nuclear together. And for the gravitation, it is a graviton. But the graviton has not been observed yet. All the others we know we have observed. And one further thing for you to know also is that in the standard model of particle physics, these two forces, electromagnetism and weak forces, are in fact understood as one force, which is called electroweak force. And in fact, it's the same processes. It is the same interaction. So finally, with all this, I go back to all the list of particles and pick up one, the sigma. And the sigma is explained as composition of elementary particles, and it interacts through the weak force by exchanging one of these W and becomes whatever, a pion and a proton. So this is the basis of particle physics. And finally, we understand all the matter that has been observed as coming from only this. So there are three doublets of particles for the quark, which makes the matter, the nucleus, and three doublets of leptons. Just take the word that they are. It's just to tell you that it's how it's organized, and all the matter can be explained with this. So two set of three doublets. Okay. Here are the mediators, and in the model there was also in 1995 the Higgs boson, which at the time hadn't been observed, and I will tell you why this was needed in the model. So what was the problem? So that was in the 60s. People had observed phenomena. That was in 1995, let's say. If you look at the particles we know, and you look here, these are the name of the elementary particle we know. So now we don't have 180 or anymore. We have 12 particles plus a mediator. Okay? And here is the mass. The mass in some unit, the mass, elementary mass of the particle. And what you see is that it's completely different for each particle. There is somehow no rule. And if you look carefully here, it's not really visible here, but this is a logarithmic scale. So they vary, they are very small particles. So for example, the neutrino, if you take the neutrino, one of the particles, to have the mass of a mosquito, the largest particle, the top quark, has the mass of a jumbo jet. So you see, really the spread is enormous, and this was not understood. The other thing that was not understood was the fact that this mediator I was talking about, for the electroweak force, for example, there are the W and the Z I mentioned, and the photon. Some are very massive, and the photon is massless. All this was not understood. So in 1964, Mr. Peter Higgs, or these two gentlemen also, François Engler and Robert Broad, and another group of people worked on the theory and created this field. It's called the field, which fills the space somehow, which makes the individual elementary particle interact with some specific rules, and the way they interact gives them the mass. Okay, that's all right. And so if you want to have a little picture of what happens, if you imagine the Higgs boson filling the space and the particle being in the space, the way it propagates inside creates the mass by interacting with this Higgs field. Okay. So that was the point, the starting point of the search for this particle, which was missing because you saw this very large diversity in masses need to be explained. Otherwise, there is something which we don't like. If we don't explain, it's not good. So, following this invention of the Higgs boson, experimentalists and theorists started to think how to see it. And so, in the model, one needs to find out whether to produce this Higgs and can it be detected. So the first steps, this is a schematic representation of what can happen to produce a Higgs boson. So I will come back to this, but you take for elementary particles and you make them collide. This is imagining they collide like this, and by a mechanism you can produce the Higgs boson. And there are different ways to produce it. And one can even compute, so if you look at the function of the possible mass of the Higgs boson, because at the time it was not known, it could be anything. As the function of the possible mass of the Higgs boson, this tells you about, it's a cross-section, but it tells you about what is the probability to produce it. So this could be computed. And it's at the level of 100 of this unit picobar. So this gives you the scale. I will show you later how it compared to other things. So one could compute how often a Higgs boson can be produced, but when it's produced, it decays immediately. So into different final states, and the different final state was either a pair of photons or a pair of Z boson or various things, with branching ratio, fraction of decays, which varies a lot. Again, as a function of the mass of the possible Higgs, what was the probability for the Higgs boson to decay, for example, in a pair of Z is like this. So 10%. Or in a pair of photons, 0.1%. So all this was known, and so the experimentalists started to think how it could be detected. And in order to do this, one uses colliders, you can collide particles, and because thanks to this equivalence between mass and energy postulated by Albert Einstein at the beginning of the 20th century, one can convert the energy given to particles to new objects following this rule. So that's where the particle physics uses particle accelerators. So voila, that was the starting point. Now we built, CERN built the Large Hadron Collider, so meaning colliding protons in order to produce the Higgs boson. Okay. I have written down some summary of what I say. I don't go through them. You can, if you're interested, remember them later. So in 1994, so about 20 years ago, it was decided to build this accelerator in order to produce the Higgs boson. Of course, it was not certain. It was probable, but not certain at all. Nevertheless, at CERN, which is, as I showed to you, on the border between Switzerland and France, there was already, since it has evolved from its foundation in 1954 to this time, 1994, a complicated complex of various accelerators. And there was already one tunnel, this tunnel I told you about, with its 27 kilometers diameter, which was colliding other type of particles, was colliding electron and positron. The decision was taken because with the electron and positron, one couldn't reach the production of the Higgs mass. We knew it would be higher energy. So we decided, the CERN decided to produce this Large Hadron Collider, which instead of colliding electron and positron, collides protons. And by the time, after having run with this previous collider, the left, one knew already that the Higgs boson mass was higher than 114.6 GeV, which is a mass unit. So whatever, we needed to go above this. Okay, once again, just to show you the complication of the thing, I believe it's important. So here now I come back to a graph similar to what I showed before, as a function of the particle mass. So we didn't know where the Higgs would be, except it would be above this. And this is cross-section of different processes. And so when we collide proton against proton, here it's the total cross-section to produce proton, but to find the Higgs boson is here, for example. Let's take this one. Between the total cross-section and the Higgs boson cross-section, there is a factor 10 to minus 10. So 1 out of 10 billion time you collide two protons, you would create a Higgs boson. So the conclusion of all this is that you need to make a lot of proton collision in order to sometime produce a Higgs boson. And yes, that's the main thing. And the energy for the collider that was decided at the time was high enough to produce a Higgs boson, but also high enough to produce things we hadn't seen before. Hoping, because today we haven't found any new things, apart from the Higgs boson. Voilà, so here is a schematic of the Large Hadron Collider, a summary of what it is. So you imagine this tunnel of 27 kilometers on the ground, where you want to accelerate proton to very high energy in order to reach, be able to produce high energy object. And so for this, one needs, so the difficulty of this accelerator is in fact one wants to bring the particles around and at the same time give them a lot of energy. You have protons, protons are just the nucleus of the hydrogen. So you strip the electron out of the hydrogen, you're left with the proton, and then you can, through electric field, accelerate it, and through magnetic field, you can bend it and make it turn so that you can give it each turn a bit more energy. At the end, the protons, they reach nearly the speed of light, but of course not the speed of light. So to do this, you need very specialized magnet, which at the end had to be a superconducting magnet in order not to use too much power, even though the total electrical power is, you see, 120 megawatt, which is about 1/8 of a nuclear power station, for example. And so these are the technical aspect of the collider. So it has to produce a magnetic field which is very high, 8 Tesla, which I think is something like 100,000 times larger than the Earth's magnetic field. In order to be supraconductive, you need to cool down helium to a temperature which is close to the absolute zero. It's 1.9 Kelvin. So it's nearly minus 270 degrees Celsius, whereas the absolute zero is minus 276 degrees Celsius. So this temperature is a bit extravagant somehow because it is colder than the temperature of the universe itself, which is 4 degrees Kelvin. So it's the largest fridge in the world. So all this to be able to not use too much power to be able to accelerate this process. And okay, so these 27 kilometer circumference are filled with 9,000 magnets, all having a little speciality, one to turn, one to accelerate, one to focus the particle. So it's a fantastic technological thing, instrument. So this is just a schematic with the two tubes where the protons, they have to circulate in two tubes and then they bring together to collide. And this is a picture, a real picture of the tunnel itself inside the Large Hadron Collider tunnel, and these are people working on very precise connectivity. This is an artist's view. As you see, this is the picture I showed at the beginning, and this is if you go 100 meters below. So 100 meters below, there is this tunnel, and now it's all well to collide protons, to create new objects, but one needs to analyze, of course, what has happened. So we have to build, and I will come to this in a moment, detectors to look at this collision. So on the LHC, the Large Hadron Collider, there are 4 experiments. There are 2 which are diametrically opposite. This Atlas experiment I mentioned already, and its sister CMS. The 2 are doing the same physics. They're there to cross-check each other somehow, because we want to be sure that if something is seen, it's not a bias from the detector having a problem. And there are 2 other experiments here, which are here and here, which are more specialized, and I'm not going to talk about that. So the next slide, I think I said the same. So I will. Now I want to bring one point to you. Is I said that we collide protons, and I've also said, or implied at least, that these protons are not elementary particles. No, I don't think I said it, sorry, I'm saying it now. So the protons, in fact, are not elementary particles. They're composed of 3 quarks, and the 3 quarks are held together to make the proton with this glue on, I think. Yes, okay, they are there, but they're not there. Between, like this. So in fact, when we make the collision of the proton, what we're really interested in the collision between elementary particles. And this is indeed what happened, because when they have a lot of energy, finally what see each other are the quarks or the gluons. And this is a schematic somehow of what happened when the 2 protons arrive. And here is the elementary particle collision. And somehow you can picture what happened like this. That you bring together a lot of stuff, and at the end, what you want to see is one of them outside. And said in other words, the 2 protons, again, we extract 2 elementary particles, produce the Higgs maybe, which will decay. And what we want to know, to build, is something which will interpret this. So we need to build a detector to look at what has been produced. And this is what I'm going to talk now about. So the experiments, and I only talk about Atlas, which I know better, as an example, but really you should take it it can be any experiment. Okay, so I skip this. So here is a schematic view of Atlas. I will say a few words here. So you imagine there is a proton which comes this way, and another one which comes this way, and they collide in the center and produce particles, whatever, and we want to look at them. So Atlas is like a giant microscope, if you want, and so we have put around the collision point very specialized detectors which can analyze precisely what has happened. So one detector looks at charged particles, another one will look at neutral particles. These big detectors at the end will look at particles which have not been absorbed by the rest, and by correlating all this information, we can come back to what happened at the collision. And so, a few pictures. So what we have built between the year 2000 and the year 2008 is a very high precision detector. This is a picture which came later, but just to illustrate of what happened when the two protons collide. And we want to distinguish what happened, which is two processes which happen with 20 microns, so 0.02 millimeter apart on a big scale. So we have constructed the various elements, and you can see there is a little man somewhere here. So the scale of the detector. So we had to build all over the world many elements to create this detector, and it's 100 million channels. So, like you said earlier, a camera is 10 megapixels, million pixels. This one is a fantastic camera with 10 times more channels. It's a bit bigger. So this is an example of when we build the detector, lowering the elements inside the cavern. And so the cavern is 100 meters underground. The detector is 50 meters long, like a swimming pool, Olympic swimming pool. It's 25 meters high, and it weighs 1 Eiffel Tower. But with this, we can measure the trajectory of the produced particle with a precision of 0.02 millimeter, and also measure the energy of the particles which have been produced with a precision of typically 1%. So that's a bit, and it's really big and really precise. And so, maybe I should have shown this to you before. This is some sketch of the cavern and how it is at Atlas. This is a picture of sun is here, the laboratory, and our experiment is here. This is Atlas, and this is above that, above the two shafts which go down to the cavern 100 meters below. These are a few. This is a picture of the cavern in 2003 when it was excavated, empty still. And then these are a few pictures of some elements that were brought in order to go down. This was a big magnet. All this was, it's big and precise. And finally, that's a view inside the detector of one element, some electronics, some cables, down. Voilà, that was for the detector, and that's the timeline of what we did. So starting from the 80s, some first discussion about whether the LHC should be built, the Large Hadron Collider should be built or not, various tests, various decisions, and at the end, the starting of operation. Voilà. And that was in 2009 when this was our Atlas control room where people were expecting the first collision. You may see a bit of tension and then was soon revealed when they indeed happened. That was a nice time. Voilà, and now let's go to the aim, the discovery, the search for the Higgs boson. And I would first like to say a few words how we manage to identify these particles. And I've taken an example. So this is a picture from the Atlas detector of one event, which is the Z boson I talked before. So this is the beam is here, and here you can see probably that there were two objects created in the detector, one here and one here. And by understanding how these objects are, we can say that one of them is an electron, one of them is a positron, and by reconstructing the mass, by combining the properties of these two objects, we conclude that these two objects have the mass of Z0, which is a known particle. We know it, it has been discovered before. So by doing this, we can then come back to what happened inside the proton somehow when they collided. By having looked at the final state, we know that a Z boson was produced, and it was that which came from the proton. So that's the way we look only at what we see in the detector and interpret by measuring different properties what happened. And this is how we looked for the Higgs boson. So I told you before that it can be produced, and it, for example, it can decay into a pair of photons. So what we did, we looked as a function of the mass. At the time, we didn't know the mass of the two photons. We can reconstruct, like I've just shown for the Z, we make the mass of two photons. And we look at the population, what is the structure. And if there was no Higgs boson, it would be like this. And there is something different. So we saw appearing a peak. So this one is like if we subtracted this curve. As a function of the mass, this is the number of events. And this is a similar distribution, but for a different final state. In the final state, there were two Z, which went to 2 times 4 electrons, 2 times 2 electrons. So we look in an event if there are 4 electrons, and again we compute the mass. And what we see is that if there was no Higgs, it would be like this. The points are the data themselves, the color thing as what we compute a priori by simulation. And what was visible is that there was an excess here. What was interesting is that the excess here, 125, was at the same place as the excess here. So there was evidence that there was something different than normal behavior. And so that was somehow said in simple words that the data need, we didn't know if it was the Higgs boson, but needs something else. And what is very important also is to say that the CMS collaboration, the other detector I was telling you about, opposite diameter, have also observed exactly the same behavior. And also observed the Higgs boson, and this is Mr. Higgs. And so here is what I show now is a little illustration. If you see, if we accelerate the 2 years of data taking we did between 2010 and 2012. Again, this is the same distribution I've just shown to you. This is a number of events. And if you look here at the date, is the 25th of March 2011. And now, if time starts to fly, we accumulate, we took data non-stop for these years, and you see the date increasing, so we're end of 2011 and now 2012, and I think you can see something appearing really above what we call the background. And that was what I showed before. So there is a clear excess. And now we also do statistics. And this distribution, again as a function of the mass on a reduced scale, show to you what is the probability that what I've just shown before could only be a fluctuation in the background. That in fact there is no new particle, but just there was some bit more event by chance at this position. And the probability that there was by chance fluctuation is something like 10 to minus 24. So it's like it's not true. It's too small to be true. No, I will skip it. So really, there was the evidence, the discovery of the new object. And so yes, then you probably followed this, I don't know, in July 2012 there was a CERN press conference, a CERN seminar, and most of the current newspapers, in particular in France, announced this. We also, of course, we published the results. And 1 year later, François Engler and Peter Higgs received the Nobel Prize for the discovery. But what is interesting, I think, is that yes, they did the theoretical discovery of the Higgs boson, but even in the Nobel words, the experiments are mentioned, because without the experiments there would be no proof. Voilà, and I want to say a few words about publication. So we publish all our results, of course. So we publish the discovery of the Higgs boson together, Atlas and the other experiment CMS. And we don't only look at the Higgs boson, the physics we do is very vast, because there are many interesting aspects to study for particle physics. And the two experiments together, they have published 700 papers. And here is a timeline, so from 2011 to end of 2014 for Atlas on its own, 353 papers. But of course, now I will tell you more. We are many people in this experiment. So the Atlas collaboration, the people who got together to build the detector and to do this physics, come from 38 countries, 177 different laboratories, and we are something like 3,000 physicists, including 1,000 students. It's spread more or less all over the world, but not completely. Africa is not really well represented, and this part of Asia neither. In France, we are seven different laboratories, 6 from CNRS and 1 from Saclay, working together, and we build together the detector. I will finish now with a few words on CERN, because without CERN we wouldn't have been able to do all this. So CERN was created 60 years ago, a bit more now, by 12 European countries, which are listed below. These are the current numbers. The 12 European countries, I will not tell you now. And today there are 21 members of CERN. And CERN is a big laboratory which employs about 2,300 people. There are also 1,600 which are not permanent people, and I think the most important is 10,000 visiting scientists, like, for example, us in CNRS. We are visiting CERN, we are not employed by CERN. And the budget is 1 billion Swiss francs per year for all the states. And CERN has a program to include more people, and so there are countries which are on the process of joining CERN or thinking about it. So this is a map of all these people again. So the blue are the member states, and the other color represent either people who are observing or wanting to join. Clearly, without this collaboration between all the countries, we couldn't have built what we built. And the key point of CERN was that it was created after the war, and it was thought about, I think, from 1949, after the war, where the European scientists had gone away and where the countries were damaged, and so some very inspired people wanted to put everybody together to work on nuclear science. So I've made a translation of the official text, but please, just my translation in English. So the organization ensures the collaboration, which I think is very important, between European states for purely scientific and fundamental nuclear research. So nuclear research is now a bit obsolete as a word, because nuclear means the nucleus of the atom. Now we work on the elementary constituent of it, and other researches in direct relation with it. And the organization abstains from any activity with military aims. And what the other very important thing is the results of experimental and theoretical studies are published and brought to knowledge for everybody. Okay, so that's been my personal feeling, that it's really a fantastic place. It's a bit magic, because I don't know, it works in a funny way, that we work together, even though we don't have a boss who tells us what to do. But all over the world, people work together, and it's visible in particular that one can hear all languages, and working there is particularly interesting. So one word about what CERN has produced outside fundamental physics, because it's a bit the work to build the detectors, to run the accelerators needs very high technology, so it has created various things, and here's a limited list. So in the 70s, they were the first to invent this touch screen that we use all the time now. And you probably know also that in the 90s is where the web was invented, the HTTP protocols. It developed some free software of simulation for detectors, many things. Supports open sources for software and hardware, free publications, and also the fact that I haven't mentioned that we need to analyze a lot of data. And so this grid, computing grid that you probably hear about, was also inspired by CERN. So now, here we are, elementary particles, so a new element has been added to the list recently. And, but it is not completely the end of the story, because in fact, I haven't told you yet, but this matter we have been studying represents only this is a diagram of the matter in the universe, only 4.6% of the universe. We know because the way the galaxy, the speed of the galaxy, one around the other, is that there is some matter that is called dark matter because we haven't seen it, it's not visible. There must be some matter there around, and this corresponds to about 24% of the universe, if we believe this. And there is another element, which is a bit more complicated, I would say, is the fact that the universe is in expansion, therefore there must be some energy, we call it dark energy, because it hasn't been seen, to explain this expansion. And this is, again, even more, 72% of the total content of the universe. So there are still many questions to answer to, and I hope CERN will continue to address this fundamental question. Voilà.